So today we're going to learn how to describe sampling distribution. So remember when we have histograms and we say describe, what's the thing that we usually go back to? SOCS, right? So it's kind of going to be that a little bit, is SOCS. So the fact that statistics from random samples have definite sampling distributions allows us to answer the following question: how trustworthy is a statistic as an estimate of the parameter? So to get a complete answer, we consider the center, shape, spread. Doesn't that sound like SOCS? Of a sampling distribution. Now I want to ask one question. Was anyone not here yesterday? Okay. So for anyone watching this video, you got to watch the 7.1a video first, because it literally is not. This is not going to make any sense if you skip lessons. But anyway, we have biased and unbiased estimators. You are going to get this incorrect. I just want to let you guys know. Remember those mistakes that you end up making on tests and quizzes? You're going to be asked that word on the AP test and on my test for my quiz. And somebody in this class is going to raise their hand and say, Mr. Reyes, what is an unbiased estimator? You never taught us that. And then I'm going to say, I'm going to show you after class when you're done with the test. Then I'm going to open up to these notes, go to the beginning of 7.1b and say it was right there. And you're going to be like, oh. So I'm trying to warn you. And so you're telling yourself right now, it's not going to be me. It's going to be someone in here. One of you is going to not be paying attention and not know what an unbiased estimator is. So how well does a sample proportion of red chips estimate the population proportion of red chips? So P equal to 0.5. If we took all possible samples of 20 chips from the population, this is just a random example, calculated P for each sample, and then found the mean of all those P values, we would get exactly 0.5. So for this reason, we would say that P hat is an unbiased estimator of P. So all this to say, okay, let's say I was wanting to get a random, or figure out, estimate, what is the average height in this room, okay? What would be the best guess? Where would you even start guessing? Now what if I took a sample of 10 of you and found the mean of that sample? Do you think using that sample mean to try to estimate all of you is better than randomly guessing? So listen to my question very carefully. Is it better to use the sample of at least, the mean of one sample over just a random guess? Yes, absolutely. So if you were trying to guess just a point estimate, just give your best educated guess of what the actual mean of the population is, the best way to do that is to take a sample and find the sample mean. Now, are you going to be correct? Probably not. But where else do you start? Right? It gives you a good starting point. So all this to say, X bar is the best estimator for mu. P hat is the best estimator for P. Because otherwise, if you don't use P hat or X bar, essentially you're just randomly guessing, right? So when we talk about what is the best unbiased educated guess, a statistic used to estimate a parameter is an unbiased estimator. So for example, X bar or P hat, using one of those to estimate mu or P, is considered unbiased because you have no control over the data of the sample. If the mean of the sampling distribution is equal to the parameter being estimated. So we'll talk about that a little bit more. But just remember that X bar goes with mu and P hat goes with P. So if we take many samples, the values of an unbiased estimator will sometimes exceed the value of the parameter, and sometimes it's going to be less. So if I was talking about the average height in this room, and I took just a random sample, sometimes you think my X bar will be a little bit higher than the actual mean? Yes. Sometimes you think it would be lower? Yes. However, because a sampling distribution of statistic is centered around the true value, we will not consistently, and that's the key word, consistently underestimate or overestimate the parameter. And that's the key word for bias. If something is biased, it's consistently overestimating or consistently underestimating something. And so when somebody says, this teacher is biased against me, what you're saying is they're consistently grading me harder than the rest of the class. It has to be consistent for it to be considered bias, because you're favoring someone. When we say there's bias on a football game, the refs are consistently being harder on one team versus the other. But let's say like the ref made like a hard call on one team, but then a couple plays later made a hard call on the other team. Would you consider that ref bias? No, it's when something's consistently going in one direction. But we need to recognize, though, that sometimes you'll be over, sometimes you'll be under, but as long as you're kind of not consistently above or below, it's considered unbiased. And so we're going to confirm that in section 7.2, that the sample proportion p hat is an unbiased estimator of the population proportion p. This is a very helpful result if we're dealing with a categorical variable. With a quantitative variable, we might be interested in estimating the population mean, median, min, max, Q1, Q3, variance, standard deviation, IQR, range. So which, if any of these, are unbiased estimators? So just remember, a biased estimator, and we'll talk about all of those later, but a biased estimator consistently over or underestimates the true population parameter. This right here is an important definition. I've seen this pop up on the actual practice AP tests. I've seen that pop up, like something about what makes something biased. And it's specifically that wording, that it consistently over or underestimates. An unbiased estimator will have the same value as the population parameter. So it's not over, it's not under. Let's flip the page once you're ready. So here's a little mock activity. And we're just going to kind of read through it. There's not really anything for us to write down, okay? So in this activity, we're going to use a population of quantitative data, or use a population of quantitative data to investigate whether a given statistic is an unbiased estimator for the corresponding population parameter. So each student should write his or her height in inches neatly on a small piece of cardstock and then place it in a bag. After your teacher has mixed the cards thoroughly, each student in the class should take a sample of 4 cards. Record the heights of the 4 chosen students, and when finished, the students should return the cards in the bag, mix them up, pass it to the next kid. So, each one of you is going to take 4 cards, record the heights on those cards, put them back in, mix it, pass it to the next person. They take 4, mix it, pass it to the next person. So basically, you're taking lots of random samples of 4. Do you agree? So each of you, and I'm just going to kind of skip what's happening. Each of you are going to calculate an X bar for your 4 numbers, correct? And then what we're going to do is we're going to take all of those X bars that you all calculated and then put them in a list. Do you understand what's going on here? So each of you has your own sample mean, and that becomes your number that you're going to present to the class. So for your simple random sample, you're going to calculate the sample mean and the sample range for the heights. So you're going to calculate the mean and the range. Then you're going to go to the board. You're going to record the heights of the 4 students, the sample mean, and the sample range, and it's going to look something like this. Now, obviously, we don't have time. We're not going to do this right now. But we're going to be, all of you are going to each have that. So would you agree that in this class we would basically have 30 different samples of size 4? And all 30 of you would have your own X bar and your own range. Say yes. Okay. Now, if we were to plot the values of the sample mean and sample range on 2 dot plots, once everyone's finished, we would find the actual population mean and the actual population range. Now, based on your approximate sampling distributions of X bar and sample range, which statistic appears to be an unbiased estimator and which appears to be biased. So when Mrs. Washington's class did the activity, this is what they got. So this was the sampling distribution of X bar. So all the kids went to the board, wrote down their X bars, and so that's the center of that graph. But then they actually got everybody's height and got the actual population mean, and they got this number. Would you say that those numbers are pretty close to each other? Absolutely. So would you say that X bar is a good estimator for mu? Yes. Now, take a look at this. Here's the sampling distribution of the range. So here's all the ranges that the kids got. In the center of it was 10.12, somewhere right there. But the actual population range was 21. So is that a good estimator? Absolutely not. Because everybody calculated their own range. The actual population range was 21, but the center, meaning the average range of everybody's list, was 10. 10 is not a good estimator for 21, right? So that's the point that this is going to say. Mrs. Washington's students decided that the sample range is a biased estimator for the population range. Why? Because the center of the sampling distribution for this statistic is 10.12, which is much less than the actual parameter of 21. So to confirm the class's conclusions, they used software to simulate taking 250 simple random samples of n equal 4 students. And for each sample, they plotted the mean height and the range, and these were the following graphs that they got. So notice here. So this, they basically reran the trial, but 250 times in a computer. And notice that this computer simulation got this center, but the actual population mean was 66. Would you say like that's pretty spot on? Yeah. But notice here, the population range was 21, so the actual population is that number over there. But this is all over the place. And would you say that it's consistently underestimating 21 or overestimating? Underestimating. So remember we talked about something is consistently underestimating or overestimating, we consider it bias. So this would be considered bias. This would be considered unbiased. Because on this one, the mean is right around here. Would you say there's some above it? Say yes. Are there some below it? Is it consistently above or below, or is it pretty well balanced? Pretty well balanced. So that's why we'd consider that unbiased. Okay, let's move on. So the next thing we're going to talk about is spread. And another word we talk about with spread is variability. So to get a trustworthy estimate of an unknown population parameter, we start by using a statistic that is an unbiased estimator. So in this case, we'd want to use X bar, the sample mean. That's a good thing to use. The sample range is not a good thing to use because it's biased, but we will use X bar. And this ensures that you won't consistently over and underestimate the parameter. Now, unfortunately, using a larger sample size does not ensure that the value of your statistic is going to be close to the actual parameter value. So the sample proportion p hat from a random sample of any size is an unbiased estimator of the population proportion p, but larger samples are more likely to produce a statistic that is closer to the true value of the parameter. Because as your sample size gets infinitely large, isn't it getting closer to the actual population? Right? So the more data you have, the closer you're going to get to the actual population, which makes sense. Larger samples give more precise estimates than smaller random samples. And even still, a larger sample does not have fixed bias. So we've talked about this, and so we're going to define this phrase variability. This is another way of saying spread. And I'm going to explain this really well in a second. But the variability of the statistic is described by the spread of its sampling distribution. So, looking here, would you consider this fairly spread out? So it has a high variability. Now, is it centered in the correct spot? Yeah, it's centered at the actual true mean, so it's not biased, but it's fairly spread out. Okay? So this spread is determined mainly by the size of the random sample. Larger samples will give smaller spreads, and the spread of a sampling distribution does not depend on how much of the size of the population, as long as the population is at least 10 times larger than the sample. We'll talk about that in a little bit, that 10 times thing. The variability of the sample, variability of the sample is controlled by the size of the sample. This has important consequences for designing samples. So it might be very well that you might need to take the same sample size to estimate the U.S. adult population as you would to sample a student population at Ohio State University with a population of 60,000. It all depends on the situation. But let me kind of give you some pictures to visualize what's happening. And I'm going to show it to you later, but I just want you to, because I think maybe right now you're like, Mr. Reyes, I have no idea what's happening. And so let me give you some imagery. So if you're on your phone right now, you need to get off your phone, because you will get so lost so quickly right now. What we've talked about are two main things. We've talked about bias, and we've talked about variability. The way I like to think about bias, imagine if you're in an archery competition. Okay, it's like you're shooting, I don't want to talk about guns, so let's talk about archery. So your bias is your aim. Your variability is your precision. So I want somebody to answer that for me. What do you think I mean by aim and by precision? So yeah, kind of like that. Imagine if you talk to Hawkeye and you tell him, I want you to. So precision is, let's say you're able to get the arrow and it's able to hit the star at the top of that tree. Okay. Could I do it again over and over and over and over and keep hitting that same spot? That's precision, right? Now aim is just, where are you aiming? So let's say my aim was off a little bit, and instead of hitting the star, I hit C-3PO, right? Was my aim off? But what if I was able to keep hitting C-3PO over and over and over and over? Even though my aim is off, my precision is high. And so I want you to think about a bullseye. And let's say we're trying to hit the bullseye. Something that's unbiased with low variability is going to look like this. Let's say I hit the bullseye and I'm aiming in the right spot and it's very precise. So there's low variability. It's really tightly compact. How would you describe, and let me make this a little bit smaller. How about this though? What if I had a bullseye and the center's right there, but all my shots were over here? How would you describe that person?
Low and high precision.
They have very high precision, but their aim is awful. So is that consistently missing the target? Is it consistently missing it in the same direction? So what would you call that? Biased. So it's got very low variability. It's not spread very much, but it's highly biased. So what could that mean is that maybe that person's really good at aiming, but maybe their scope is off. So maybe in their scope, they're aiming at the target, but when they let go, it's going off somewhere else. So it's just not aimed correctly. That happens. So I don't know if you've ever seen snipers. They have to adjust for the wind, and maybe the wind's going a certain direction, so they're aiming at a spot, but it goes like somewhere else. So that happens in like Call of Duty and stuff like that. Now, let's talk about this person here. What is happening with that person? Let's use the word aim and precision. All those dots, where's the center of all those dots? Is it the target? The center of the dots. If you were to take the center, they were aiming in the right spot. So their aim was correct, but were they precise? No, their shots were all over the place. Some of them were too high, some of them were too low, some of them to the left, some of them were to the right, but it was all centered around this spot. And some of you may be suspicious of what I'm trying to say right now. And so my next picture is going to make a lot more sense. All those are spread out. That person aimed in the right spot. They just have very awful precision because their shots are everywhere. And then the last picture is this one. There's the center of the target. And this is what happened to the shots. How would you describe this person? Does it even look like they were aiming for the target? No, they were not. So they have low precision, but highly biased because they're aiming in the wrong spot, and it's all over the place. So do you kind of see what I'm talking? And that's what we're kind of talking about with spread and with bias. So you have very low bias, high precision. So low bias, low variability. High bias, low variability. Low bias, high variability. High bias and high variability. We'll label that all in like 2 pages. Go ahead.
Just like on the last one, because never mind. I was just about to say, like, even though it's spread out, right, so it's not necessarily precise because it's so spread out, it's still kind of consistently to the right of the target.
Which means it's highly biased.
Highly biased. But if you have
You got it?
Yeah.
It clicked?
Yeah.
So this has high bias because it's all over the place, right? But in the same direction. So you almost look at this person and you're like, you were aiming for, like, this person was clearly aiming somewhere, right? They weren't just shooting those arrows randomly. Like, they're clearly aiming somewhere, and it's not the center. Like, they're aiming somewhere else. So let's take a look at this. The histogram to the right shows the intervals and minutes between eruptions of the Old Faithful geyser for all 222 recorded eruptions during a particular month. For this population, the median is 75 minutes. We use Fathom software to take 500 simple random samples of size 10 from the population. The 500 values of the sample median are displayed in the histogram on the right, and the mean of these 500 is 73.5. Okay, so these are the medians right here. So from the 500 samples. Is the sample median an unbiased estimator of the population median? So here's the actual population data, I believe. The actual median, where's the actual middle? I would say maybe somewhere like here, right? Ish, maybe. Well, does it say what the actual median is? Oh, it says the actual median right here. What's the actual median? 75. Yeah, so it's 75. But over here, so the median here tells us is 75. But over here, the median is, well, it says the mean, but it's like the mean of the median. So it's like it's 73.5. So, would you say that the sample median is an unbiased estimator of the population median? This one's kind of tough because they're pretty close to each other, but is it close enough? Is it close enough? Because my answer key says that the median does not appear to be an unbiased estimator because the mean of the sampling distribution is not equal to the median. So the idea for it to be unbiased, especially since we did this 500 times, if you did it once or twice, would you expect it to be equal? No. But if you did it 500 times, we go back to what we wrote over here. An unbiased estimator will have the same value as the population parameter. Is that true in this case? Does 75 equal 73.5? No. So no, because the mean of the approximate, we should probably write this down so we have something to reference later. The mean of the approximate sampling distribution of the sample medians is not equal to the population median. Suppose we had taken samples of size 20 instead of size 10. Would the spread of the sampling distribution be smaller, larger, or about the same? So now we're talking about spread or variability. So let's go to the last page and what did it say about spread? And let's look at this here. A sample proportion. So basically, larger samples are more likely to produce a statistic that's closer to the true value. So basically, the bigger your sample size, the closer it's going to center around the actual statistic. And so what does that mean? Remember the example we did up here where everybody grabbed like 4 heights and then found the sample mean, grabbed 4, found the sample mean. The sample size for this was 4. It doesn't matter how many times you repeat it, it's a sample size was 4. If we had each one of you grab like 10 names and then find the average, or grab 20 names, the bigger each individual sample is, the more precise it's going to be. It doesn't matter how many times it's repeated. What matters is how big is the sample each time it's repeated. So, going back to this question, suppose we'd taken samples of size 20 instead of size 10, what would happen to the spread? Would it get more spread out, less spread out, or stay the same? It would get smaller. Because, and let me see what, because we would have a more precise estimate, or more precise estimate. That's fine. Okay, let's look at the next one. Describe the shape of the sampling distribution. So we're specifically looking at that. That's the shape of the sampling distribution. What would you guys think? Yeah, it's unimodal and skewed left. All right, perfect. These next 2 pages are fairly quick. So this was originally a 4-page lesson like it normally is. I just pushed enter a bunch of times to spread things out. So it's not really like a super mega long lesson. It just feels like it. So we're going to be able to like fly through this page because I kind of already explained it to you. But we can think of the true value of the population parameter as the bullseye on target. And of the sample statistic as an arrow fired at the target. Does this sound like what I already talked about with you all? So both bias and variability describe what happens when we take many shots at the target. So bias means that our aim is off and we consistently miss the bullseye in the same direction. So it's not about just missing and it's everywhere. It's that you keep missing but to the left. Or you keep missing to the right. You keep missing in the same direction. So bias concerns the center of the sampling distribution. Where you can tell where a person's aiming. They just keep missing in the same direction. So it's like their aim is just off. Variability means that repeated shots are widely scattered on the target. So repeated samples do not get very similar results. Ideally, we would want estimates to be accurate, which is unbiased, and precise, meaning having low variability. So let's go ahead and draw what each of these situations would be. This is a point where people might go crazy. Please don't go crazy. You're going to know what I mean in about 20 seconds. Okay? So, what does high bias, low variability mean? So high bias means your aim is off in the same direction. Low variability means that it's very closely packed together. So it would be something like this. I want to see if I can change that color so it stands out a little more. What looks best? That blue one? I think that's good. Okay. Now low bias and high variability. So if the bias is low, it means they're aiming in the right spot. So it's going to be around the center. It's all spread out around the center. So it's going to look something like this. So we were right here, correct? It's in the center now, but really spread out. Let me make these a little bit smaller. Does that kind of make sense? And then high bias, high variability. What's that going to look like? I'm trying to find a good color. It doesn't seem to be showing up very well on that. No. Maybe this one. Oh, that's good. Okay, so high bias, high variability. So it's like something over here where you're like, this person is not even aiming in the right spot. And it's all spread out too. So like, where are you aiming? Right? Are they aiming for the center? No. So the aim is completely off and it's way spread out. So ideally, what you want is low bias and low variability, which looks like this. Oh, white would have been really good. Should have changed everything to white. Okay, it's fine. Any questions there on those 4 scenarios? Okay, so given a choice to estimate an unknown parameter, we want to choose one that has no or low bias and minimum variability. Now, shape is a little more complicated of an issue. So we've seen that sampling distributions that are left skewed, we've seen some right skewed, we've seen symmetric, we've seen normal. The same statistic can have sampling distributions with different shapes depending on the population and the sample size. We will talk about that more in later chapters. or in later sections. But let's go to our last page and then we're all done. Well, so don't stay on this page, but I want to just explain how do you fix bias? Let's talk. I just want to talk about that because clearly, like, these are all different issues, right? So, like, if you have high bias, high variability, or you have low bias, like, how do you fix those issues? Let me just talk about that just really quick. You don't need to write this down. So, how you fix bias is using the right estimator. So, like, if you're using the sample range, we saw that the sample range is consistently aiming to the wrong number. Like, and we saw that here, right here, that the actual true range is 21, but it was consistently underestimating it. So the issue with bias, the only way you fix it is you have to be using the right thing to begin with. And so we found, like, using X bar, the sample mean, that's a good thing to use from the beginning. And so if you use the right estimator, your bias is going to fix itself. So what are correct estimators? The only two we're really going to be using in this class are X bar and P hat. So as long as you're using X bar and P hat, you know that your bias situation is fixed. So how do we fix variability? So let's say you have this situation where you have really high variability, but you want to change it to low variability. How do you fix that? That's 100% correct. The sample size that you start with. So there's actually a magic number that we're going to learn later on that as long as it's bigger than this number, we know that the variability is going to fix itself and we're good to go. We're going to learn that later, but basically you want to use the right estimator with a large enough sample size, and then you will always have the ideal situation. Now, how do you do that? This is what we're going to be learning in this chapter. Okay, last page. You write the population values 1, 3, 5, 7 on slips of paper and put them in a box. Then you randomly choose 2 slips of paper with replacement. The mean of the population is mu is equal to 4, and the range of the population is 6. List all possible samples of size n equal 2 and calculate X bar for each of them. This means form a sampling distribution for the sample means. So, there's going to be a lot of writing that we have right now. Just trust what I'm about to do. And we're going to write something down that it isn't actually asking us to do, but we're going to need it for part C. So you're going to write sample. You're going to write sample mean, which is X bar. And then you're going to write sample range. And you're going to write it again. Sample mean sample range. So we need to come up with all possible combos of 1, 3, 5, 7 that are size 2 with repetition. So you may think, Mr. Reyes, I have no idea what's happening. 1, 1. 1, 3. 1, 5. 1, 7. What are the next ones I could write? 3, 1. 3, 3. 3, 5. 3, 7. Are there more samples? Tell me the next one. 5, 1. 5, 3. 5, 5. 5, 7. And my last one? My last 4, basically. Yeah, 7, 1. 7, 3. 7, 5. 7, 7. Okay. Let's go ahead and find the sample mean for each of those. We're going to just kind of do it in our head really quick to not make this too complicated. So like if you got the mean of 1, 1, like what's 1 plus 1 divided by 2? 1. 1 and 3, what's 1 plus 3 divided by 2? 2. Okay. 1 plus 5 divided by 2. 3, and then 4. Now we got 3, 1. So 3 plus 1 divided by 2. 2. Okay. Oh, guys, this is AP stats. 4 and 5, right? And how about my sample means over there? 5 and 1. 5, 6 divided by 2 though. 3. So 3, 4, 5, 6. And then the last ones? 4, 5, 6, 7. Okay, just leave it there for now. So now it says make a graph of the sampling distribution of X bar. What do you see? It should say X bar. I think it does say X bar actually. So what were the possible values that popped up for X bar? 1 through 7. Okay. How many times did 1 occur? Once. So why don't we draw in here and go like count on the side. And we'll do like 1, 2, 3, 4, 5. Okay. So 1 happened once. How many times did 2 happen? Twice. How many times did 3 happen? Let's see. We got to count. 1, then 2, 1, 2, 3. So 3 times. How many times did 4 happen? 1, 2, 3, 4. How many times did 5 happen? 5 times? Ooh, 3 times. 1, 2, 3. Then 2, then 1. So that's 1, 2, 3, 4, 5, 6, 7. And that's X bar. What do you see? Okay. It's a normal centered at 4. It's normal and centered at 4. Well, what would the actual population mean? 4. So is that a good estimator for, were they aiming in the right spot? Absolutely. Absolutely. So this would be considered an unbiased estimator. Now let's do the same thing for the ranges. So remember, it's going to be max minus min, max minus min, max minus min, max minus min. So what we get here is 0, 2, 4, 6, 2, 0, 2, 4, 4, 2, 0, 2, 6, 4, 2, 0. Now you see why I had you finish up that table, right? So it wants us to make a graph of this. So the same thing, just like we did for the mean. And 1, 2, 3, 4, 5, 6. I think we're actually getting around time. This one's really not that important, but how many times does 0 happen? 4 times. So that's 0. Then 2, 1, 2, 3, 4, 5, 6. And 4, 1, 2, 3, 4. And then 6, 1, 2. Does that look like a good estimator of the actual range? because the actual range is 6, but it's centered at 2. Does that feel good? No, this is biased. All right, kids, the bell's about to ring, so you all have a great day.